Hello students, welcome to FosterJEE. This is our third lecture for the chapter Current Electricity. In the last lecture, we have discussed basic concepts about drift velocity, relaxation time, and we have completed Ohm's law. Now, we also did some numericals based on resistance and its calculation. Also, I have given you one homework problem to solve. So let's go to that problem. So here is our problem, in which we have a cylinder which is hollow from inside and inner radius is A and outer radius is B. Also the resistivity of the material of the cylinder is rho. In first part we have to find the resistance between I and O, that is this part and this part. So now let's see how to proceed. Let's first of all see this diagram from the top, that is from this side. So it will look like this, where this is the cylinder, this is the hollow cavity. Now the inner radius is A and the outer radius is B. Now first of all, it's clear that we have to find the resistance between if this face, inner face, and this outer face. This is our outer face and this is our inner face. Now first of all, let's see how the current will flow. Now if we apply potential difference, or the charge is allowed to go from this face to this face, the charge will flow radially outwards from all the possible ways. So in other words, this length of the cylinder will be responsible for the resistance. Now let's remove this diagram. Now this is inner radius A and this is outer radius B. Now since at every point of traveling the charge from this face to this face, the cross sectional area is changing. How we can say that? Because at a surface very close to the inner surface, the cross sectional area will be 2 pi A into L, where L is the length of cylinder, and at the outer part the curved surface area is 2 pi BL. So it is definitely not same. So we have to apply integration. For integration, we will take up an element from the center. Now if we take up an element at a distance r, it will be of thickness dr. Now let's draw this cylinder, which is an elementary cylinder, into 3D and see how it will look like properly. Now in 3D it will look like this. Here we can see we have a complete cylinder which is hollow from inside, and we have taken an element from the center at a distance r, and it will be something like this. So it will be a kind of cylinder only, and we have drawn this cylinder properly here. Its radius is r and thickness is dr. Now our whole focus will be on this. Now what will be the small resistance due to this elementary cylinder? And we know that is small resistance is always given by rho dr upon area, because resistance is given by rho L upon A, where L is the length of flow and A is the cross sectional area through which the charge is passing. In case of cylinder, we can see the charge will enter from here and will leave from here. So what will be the length of flow? That is dr only. So we have put in place of L dr, and A, where A is the area of cross section, A is given by this cross sectional area, this whole cross sectional area. This is given by the curved surface area of the cylinder, which is 2 pi r if this is L as given in the question. So it becomes 2 pi r L. Hence, dr can be written as rho dr upon 2 pi rl. Further, we can write it as dr is equal to rho upon 2 pi l dr upon r. Now we can see L is constant and rho is also constant, but r is varying. So we will integrate this equation. When r was equal to a, that is, this r is equal to this a. At that time, no element was being covered because this is hollow from inside. This cylinder is hollow from inside. So when r was equal to a, no element was being considered, and hence the resistance offered by this cylinder or material is 0. So when r was a, resistance was 0, and when r was b, whole of the hollow cylinder is covered. So we need that resistance. Solving this, we will get r is equal to rho by 2 pi l ln of b upon a, because integration of dx upon x is ln x, where ln is natural log. Hence, this is the resistance offered by a cylinder between inner and outer face. So RIO is equal to this expression, which is rho by 2 pi L ln of B upon A. And now we have to find RAB, that is the resistance when the charge flows from A to B, that is like this. So this is very simple. Let's see. Now, when the resistance was connected or the charge is flown from this part, now notice that this is hollow. So what will be the length of flow of charge? That will be equal to the length of cylinder, that is this length, which is L. Why? Because if a charge starts from here, it will go to this part and will travel whole length A. Hence, in this case, the resistance will be given by rho L upon A. Now, L is equal to L only here. But area, what is the area of cross section through which the charge is being passed? So, we will see that all of this area is responsible for transporting the charge. So, we will take this area. Hence, area of cross section of this part will be pi of B square minus A square. Why? Because the area of the outer cylinder, that is of radius B, is pi B square, and the area of inner cylinder of radius A is pi A square. So we will subtract both of these to get the net area. So in this case, the resistance is A. So we will write RAB is equal to rho upon pi B square minus A square into L. So in this way, we can see that the resistance is dependent upon the geometry chosen and also how the charge is being flown. Now we will start our new topic, which is electromotive force. Electromotive force, which is also called EMF. Now, to understand EMF of a cell, we will use the analogy of water tank system. Suppose we have this type of system. where this is an overhead tank and this is groundwater tank. Groundwater tank. Now, if we fill water in this, then it will be automatically travel from high potential to low potential. That is, this part is having high altitude, that is high gravitational potential. So it will flow with the effect of gravity. So can we say that no external force other than gravity is to be provided to this water so that it comes from the top to bottom? Yes. But once this water gets accumulated in this, first up to this level, then up to this, and once this. Now, once it reaches this level, that is little above the pipe. So now the water is completely in this lower tank. Now can we say that this water will get traveled from this point to this point, that is like this, and will transfer to the overhead tank? No. For doing this, we have to provide any pump. This is pump. So that this water can be traveled from lower part to the upper part. In technical terms, this tank is at higher potential and this tank is at lower potential. So technically saying that water from higher potential travels to the lower potential, but water from lower potential needs some external agent, that is pump, which is here. We will write here it is external agent. External agent. So from lower potential to higher potential, if we want to transfer the water, we need an external agent, which is pump in this case. Coming to the electrical circuits, suppose we have an electrical circuit like this, where this is the resistance R and this is a battery. This is the symbol of battery first of all. Now, this higher or the longer plate corresponds to higher potential and this smaller plate corresponds to negative potential, similar like this. So we will see that if we remove the internal portions, then the final end longer part is at high potential and this part is at lower potential. So the current will flow from high potential and will travel from resistor and then again get back to the lower potential. So here also we can see from the wires the current is automatically being transferred from higher potential to lower potential. We don't want battery here also. We just want the potential difference. So if any point that is, suppose this point is at higher potential than this point, so current will start flowing from higher potential to lower potential. What is the role of battery here? That we will see. It is okay that in the circuit the current is flowing from higher potential to lower potential, but let's see inside the battery what is happening. Inside the battery we can see the charge is flowing like this. So this is negative potential or lower potential and this is higher potential. So inside the battery charge flows from lower potential to high potential. This is an important statement. Now inside the battery the charge is flowing from negative potential to positive terminal. So there has to be some external force which is doing this, because the nature of charge or the basic behavior of the charge is to travel from high potential to lower potential, but inside the battery the reverse is happening. So there has to be some external force, and hence we will write the influence that makes current flow from lower potential to higher potential is called EMF. This is the definition of EMF. So what we have concluded, that external agent that is leading the current travel from lower potential to higher potential is EMF. So the work pump is doing here is replaced by EMF of cell in a circuit. This is here the external agent. I hope this is clear. Now, if work W is done by battery in taking a charge Q from negative terminal to positive terminal, or else we can also say lower potential to high potential, then work done by the battery per unit charge is called EMF of battery, EMF E of battery. This is also the definition of EMF. From electrostatics, we have seen that E, that is EMF, it is defined as the work done in taking unit charge. Why? Because from electrostatics we have seen that the potential or the change in potential is given by work done in taking unit charge. So here, if battery has some potential difference, now from lower potential to higher potential, if we have to take some charge, then there has to be a work that is to be performed. So this is that work, and if that work is for unit charge, this E is called EMF. Now here I would like to clear up a point, that the name electromotive force is misleading in the sense that EMF is not a force, it is rather the work done per unit charge. Per unit charge. And from electrostatics, the work done per unit charge is called potential. So, it will also have same SI unit as of potential, which is SI unit is volt. Now this completes our basic of EMF. Now we will move to next topic, which is Kirchhoff's law. Kirchhoff's laws. Now let's understand the background regarding these laws. In simple circuits like this, in which a battery is connected and a resistance is also connected. Suppose this is 6 volt battery and this is 3 ohm resistor. For this we will simply use Ohm's law, which is the mathematical expression for Ohm's law is V is equal to IR. Since V is given as 6, I is to be calculated, the resistance is 3. So I comes out to be 2 ampere. So this 2 ampere will travel from high potential to lower potential and like this to this circuit 2 ampere. Moreover, in circuits like this, in which we have multiple batteries, first is like this and the second is like this, and we have a resistor, which is, suppose the resistance is 2 ohm and this battery is 10 volts and this battery is 6 volts. Here we use V equals to IR, and since V is the net voltage or net EMF, so the net EMF of these two can be replaced by higher minus lower. Now, why minus? Because they are oppositely oriented. This will tend to send charge in this direction and this will tend to send charge in this direction. So the net of 2, that is 10 minus 6, will be 4 volts, and this is simpler wire. So here we can write 4 equals to I times of 2, which is equal to I equals to 2 ampere. So 2 ampere will flow like this. Let's suppose if this battery was 10 volt and a 6 volt battery is attached like this, so that both the batteries will tend to send charge in the same direction. In that case, V net will be 10 plus 6, 10 plus 6, which is 16. So this can also be a case, but this is for this, where the batteries were oppositely oriented. A third case can also arise, like suppose here a resistance of 6 ohm is placed and a battery of 10 volt is provided, and also here one more battery of 5 volt is present, and we have one more resistance of 4 ohm. In that case, we will simply use V net equals to I times of R net, or the total current in the circuit is given by net EMF or voltage upon net resistance. For instance, we can see, or this we have also learnt in our elementary classes, that these resistances are in series. So the net resistance will be simply 6 plus 4, which is 10. Now we will discuss resistance in parallel and series in very deep in upcoming slides. But for now, let's see that or the total resistance is 10 ohm. And also the net EMF in this case will be, since this battery wants to send charge in this direction and this battery wants to send the charge in this direction, so both are opposing. So we will subtract higher potential from higher battery EMF from lower EMF battery. So in this case the net EMF will be 5, 10 minus 5 upon net resistance is 10. So the current will be 0.5 ampere and the direction of flow is like this. Now before moving to the Kirchhoff's law, let's discuss in depth about resistances in series and parallel. First, resistance in series. In series, the combination is like this. Here we have one resistance, let us suppose R1, and another resistance, let us suppose R2. We also have a voltage V. Now, this will send current in this direction. Now, a very basic method of seeing whether resistances are in series or parallel is that see the current. If current is same in both the resistances, then the resistors can be said to be connected in series. We will compare resistance in series and parallel and see how they differentiate. But for now, we can see if this current is I flowing through this battery, then this current has to travel through both the resistances. Now, this current can't be destroyed because current, what is current? Current is the charge per unit time. So, if we say that here current is I1 or I, then here current gets changed after traveling through this resistor. Then it becomes some another value, that is, let us suppose I0. Then I has to be equal to I0. If not, then we are saying that the charge is getting destroyed with respect to time after traveling through the resistor, which is impossible. So I has to be equal to I0, which means all of this current will travel through this resistor and then through this resistor, and after traveling the net current will be still I. So if this is the case, when both the resistors receive the same current, in that case both will be said to be connected in series. Now it was obvious for current that it will be same for both resistor, but the potential difference across the both resistor, we can't say that it is equal or unequal. So let us suppose across VR, so across R1 resistor the potential is V1 and across R2 resistor the potential is V2. So we can see that the total potential or the total potential difference has to be equal to the sum of potential differences across both the resistors, that is V1 equals to V equals to V1 plus V2. Applying Ohm's law for first resistor, we will get V1 equals to IR1, and for the second resistor it will be V2 equals to IR2. Plug in this into this equation, we will get V equals to I times of R1 plus R2. Now forget about these two resistors. Let's draw another diagram. Now if we have a same potential of V and we require same current I, then we need some resistor R. Then the value of that resistor will be, we will get from V equals to IR, and R will be equal to V upon I. So if we put the value of V in this equation, we will get IR equals to I times of R1 plus R2, which suggests that R equals to R1 plus R2. Now note that we have just replaced this part of the circuit with another resistance R, keeping all the other things, the voltage, the current, to be same. So can we say that R is the combination of these two, or else R is the equivalent of R1 and R2? So we can see if n number of resistors are connected in series, suppose like this. Let us suppose this is R1, this is R2, this is R3, and this goes up to, let's suppose this is Rn. Then the net equivalent resistance that will be replaced by this, let's suppose that is R net. So in series, since these are in series, that all the current, that is I, that is entering will be exited also. So the current is same. So all the resistance are in series, and the net resistance in series is given by R net equals to R1 plus R2 plus R3 plus up to Rn. Now this is the result for series arrangement of resistor. Let's move to the parallel combination of resistor or resistors in parallel. For parallel, let's draw the circuit. Suppose this is a circuit where we have a battery of total potential is V, and it sends current of I into the circuit. Now if somebody asks what is the potential difference between both these resistors, let's understand what to answer. Now forget about this part. We can see that this is a common or very simple circuit in which one battery is there and one resistor is there. So we will say that the potential across this resistor is nothing but V. Now considering the other case, now suppose this resistor is not there. In that case, we can see that this is also a very simple circuit in which one battery is present and one resistor is present. So what will be the potential across the resistor? That will be V only. So now let's combine both these circuits. So if individually the potential across both the resistor was V, in this case also the potential is V. Suppose this is R1 and this is R2. There is one more trick of seeing this, that what will be the potential across these 2 points? That will be V. This is plus V and this is 0. So the potential difference is V minus 0, that is V. Similarly, what will be the potential difference across these 2 points? That will be V only. Now let's remove these points. Now what will be the potential across these 2 points? Since it's connected to the battery, the potential difference across the battery is the same as V. Now if the potential difference across point C and B is V, then both the resistors are connected across same potential difference. So both the resistor will be at the same potential difference, that is V. So we can write in parallel combination of resistors, the potential difference across both the resistors is same. Hence, this is the criteria of seeing whether the resistors are in parallel or not. So, in parallel, the potential difference will be same. Now, we can't say about the current. So, let's suppose here current goes I1 and here current goes I2. Applying V equals to IR for R1 resistor, we will get V equals to I1 R1. For the second resistor, it will be I2 R2 since potential is same. Now, if we replace this circuit with a common circuit having only one resistor, that is R or R net. Let's suppose this is R, then this is V, and let us suppose it sends the same current I. So, the only part that is changed this one. Hence, applying V equals to IR for this circuit, we will get V equals to IR. And also from here we can see net current is being distributed with I1 and I2. So from this circuit we will get I equals to I1 plus I2. Now let's compute the values. For I, it is V by R from this equation equals to I1 from this equation V by R1 plus I2, that is from this equation, it is V by R2. Cancelling all V terms, we will get 1 by R equals to 1 by R1 plus 1 by R2. So this is the net resistance in parallel. Now let's generalize this case. Suppose this is a network where this point is A and this point is B. We have number of resistors in between these. Suppose this resistor is R1, this is R2, R3, R4 and so on. It will be continued to Rn. Now, if it will be replaced by a single resistor, then the value of that resistor, let's suppose that is R net. And from above expression, we can say that the net resistance is given by 1 by R net equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus dot 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 up to 1 upon Rn. We can write it in the lower portion plus R3 1 by R3 plus up to 1 by Rn. So this is the result for parallel combination of resistors. I hope this is clear. Now we will take up a very simple example to illustrate what we have studied. Suppose we have a circuit like this, and here we have 18-volt battery. Here we have a resistor of 4 ohm resistance. Here we have a resistor of 6 ohm, and here we have a resistor of 3 ohm. Then we can see that if this point has some potential and this point has some potential, then the potential difference between both these resistors will be same. Hence, can we say that these two resistors are in parallel? So, the net of these two resistors, R net, will be given by 1 upon R net plus 1 upon R1, that is 6, plus 1 upon R2, that is 3, which gives R net on solving equals to 2 ohm. Hence, this circuit can be reduced to here a battery will be of 18 volts, and this resistor is 4 ohms, and this resistor is 2 ohms. Now, simple that these two resistors are in series, because if current is generated from this, then it will have to travel from both these resistors. So, these two are in series. So, in series, the net resistance is given by R net equals to R1 plus R2, that is 4 plus 2, which is 6 ohm. So, our final circuit becomes like this, where this is 18 volt battery and this is a 6 ohm resistor. Applying V equals to IR here, V equals to IR, you will get 18 equals to I into 6, that is I equals to 3 ohm, 3 ampere. So, in this circuit, we will say a 3 ampere current will be drawn from this battery, and that will be going into the circuit. Now, let's see one more interesting problem based on net equivalent resistance. Suppose this is the problem we have. Now, we have to find the resistance between A and B, RAB. First of all, we will see that part of the problem where it is obvious to say that either the resistances are in series or parallel. So, we can see that these two resistors are in series, because if current I enters in this branch, then it will has to leave this branch. So, same current is passing, so these two have the resistors in series. Now, resistors in series, that means the net resistor will be the sum of the two resistor. So, this can be replaced by a single resistor of 3 plus 3, that is 6 ohm. Now, we can see that across these two branches there are only two resistors, hence these are in parallel. Since these two are in parallel, let's take up a moment to see what happens in parallel when two resistors of equal resistances are connected. Net resistance is given by 1 upon R1 plus 1 upon R2. If R1 equals to R2, in that case 1 upon R net is equal to 1 upon, say it is R, this becomes 1 upon R plus 1 upon R, which becomes the R net equals to R upon 2. Hence, if the resistors are in parallel and the resistance value is equal, in that case that equivalent resistance becomes half of the one resistor. So, we can see that these two resistors are in parallel and these are equal in magnitude. So, if we combine both these, then we can replace this branch with resistor equal to, since both are equal, the resistance becomes half of the one, that is 3 ohm. Now, we can easily see that these two resistors are in series now. So, the combination of these two will be like this. Since they both were in series, then 3 plus 3 becomes 6. Again, these two branches are in parallel and the resistance are equal. So, we can replace both this resistor with one resistor of 3, 3 ohms, that is 6 upon 2. Again, we can see these two resistors are in series. So, we can replace both the resistors with a single resistor of 6 ohm. Again, these two resistors are in parallel and are equal. So the net is half of the one resistor, that is 3 ohm. Again, we can see these two resistors are in series. So the net resistance will be 3 plus 3, that is 6. Now we are arrived at this position. So this can be easily rewritten as, here we have one branch and here we have another branch. The lower resistance is 3 ohm and the upper resistor is 6 ohm, and we have to find the resistance, net resistance between these 2 points. So we can see between these two resistors are in parallel. So 1 upon R net becomes 1 by 6 plus 1 by 3. So R net is equal to 2 ohm, which is the answer for the original problem. Also, we will find many more problems like this. Suppose we have this point A and this point is B. All the resistors have same resistance value, that is R. We have to find the resistance between A and B. So, how will we proceed? In these cases, it is advised to first analyze every portion, that is every junction. Now, what is the potential of, if this point has potential VA, then what is the potential of this point? This is also VA. This point is also VA. So similarly, this point is also VA and this point is also VA. Let's remove all other points. This point has a potential of VA. Similarly, if this point has a potential VB, this point has the potential VB, this will also have potential VB, and similarly this will also have potential of VB. Let's remove all the intermediates. Now we are arrived at a point where, suppose we have 2 points A and B, and the potential at B is VB and the potential at A is VA. Now between A and B we have one resistor, that is between A and B we have one resistor. So let's connect. This is our that resistor. Again, between B and A we have one more resistor. So let's connect one more resistor. Again, between A and B we have one more resistor. So a total of 3 resistors are present. So we will draw one more resistor over here. Now all these resistors have value R. So we have to evaluate the resistance between A and B, which will be RAB, since all the resistors are connected by same 2 points and the potential difference across these are same. So we can say these are in parallel. So for RAB we have to use the parallel combination expression, that is 1 upon R plus 1 upon R plus 1 upon R, which is 3 upon R. Hence RAB comes out to be R upon 3. Hence the net resistance of this type of question is this. Now we will solve many more problems on parallel and series combination, but let's now first come to Kirchhoff's law. Kirchhoff's laws. So far we have seen series and parallel combination of some circuits, but not all the circuits can be easily reduced to simple series and parallel combination. For example, circuit like this. Suppose this is R1, this is R2, and this is R3. This is first battery of EMF1 and this is second battery of EMF2. Now, can we say that suppose if we want to calculate the net resistance between these 2 points, let's say this is A and this is B. So, can we say that the net resistance is simply the parallel combination? No. Why? Let's understand. When we don't have batteries, we can easily say that these resistors R1, R2 and R3 are in parallel if we have to evaluate across these 2 points. Why? Because all these branches are at same potential difference, that is VA minus VB. But here, because of the presence of these batteries, there will be some different potential difference across each resistor. Suppose this point has potential VA and this point has potential VB. Then potential across VR, that is the potential across third resistance R3, let's suppose that is V3, is VA minus VB. But the potential across this branch, this whole branch, is VA minus VB. That's true. Whole branch is VA minus VB. But we have to see across this resistor. Because of this presence of battery, the potential difference across R2 will be some other quantity than VA minus VB, which will have the contribution of E2 also. Similarly, for first branch, this whole branch will have the potential difference of VA minus VB, but this resistor R1 will have some effect of E1 also. Now, what effect do it have? That is dealt in Kirchhoff's law. So, now I hope it's clear that how or why this circuit can't be easily broken into series and parallel combinations. To solve such complex circuits, we use Kirchhoff's laws. Now, there are two Kirchhoff's laws. Two Kirchhoff's, or there are two laws. First law is called Kirchhoff's Junction Law. Junction Law. Suppose this is a part of circuit we have. Now this point is called junction. Now let's suppose from this part of the circuit or this wire, I1 current is coming. From this branch, I2 current is coming, and here in this branch, I3 current is going, and here in this branch, I4 current is going. So the Kirchhoff junction law says that summation of current at junction has to be 0, which is even logical, because what is current? Current is basically the rate of change of charge. So if net current, that is incoming current, is not equal to outgoing current, then it means that the junction will store some charge, which is not the property of conductor. Hence, for this example, let's apply the Kirchhoff junction law here. So incoming current towards the junction is I1 plus I2. Now, outgoing current from this junction is I3 equals to I3 plus I4. Hence, the statement is basically incoming current equals to outgoing current. So we can also mention a point that this law or junction law is based on conservation of charge. Conservation of electric charge, as charge cannot be created nor be destroyed. That is, if incoming current is not equal to outgoing current, then it means it is violating the law of conservation of charge, which is not possible. Now, this completes our Kirchhoff Junction Law. Our second law is Kirchhoff's loop law. And its statement is given as the algebraic sum of the potential differences in any loop including those associated EMFs and those of resistive elements must equal to 0 or must equal 0. Mathematically, we can say that this means summation of potentials differences across a closed loop is 0. Also, to understand the application of this law, we have to keep in mind some points. Suppose we have two situations. This is point A, this is point B, this is point A, this is point B. The EMF of this battery is E, and in this battery is E. But the polarity or the way in which the battery is connected in the circuit is opposite in both the circuits. In this case, if we say that we have to move along this path, that is from A to B, then while calculating the potential difference, which is final minus initial, so final destination is B. So this is VB minus VA, which is equal to, now see, B is at higher potential. Why? Because it is connected to the positive terminal of battery. Similarly, A is connected to the negative terminal of battery. Hence, A is at lower potential and B is at higher potential. So, VB minus VA is E, that is positive of E. In this case, we have to calculate the potential difference. The potential difference is given by final potential minus initial potential, that is VB minus VA. That depends upon the path. Now, note that in this case, B is connected to the negative terminal of battery, that is lower potential, and A is connected to the positive terminal of battery. So, VB minus VA has to be negative. So, this becomes minus E. Hence, we can conclude that if we are moving in the direction of increasing potential, that is, A is at lower potential and we are moved from A to B, then the potential difference is positive or potential is increased. Similarly, if we are moved from higher potential to lower potential, that means the potential will decrease. So the potential difference is negative. Simple. One more case. Suppose we have two cases of resistors in which in A part current is flowing from A to B and in second part current is flowing from B to A. Now if we move along this path, that is from A to B, in that case what will we report? We will report the potential difference. Potential difference delta V is VB minus VA. Now here we have to see that current always flows from higher potential to lower potential. Since it is flowing from A to B, that means A has to be of higher potential. So the potential difference VB minus VA, since A is higher, B is lower. In that case, if we move from A to B, then VB minus VA is negative, and it is negative of I times of R from V equals to IR. Similarly, if the current is traveling like this, the current always travels from high potential to lower potential. Hence, B is at higher potential and the path is like this. So, if we want to calculate the potential difference, that is VB minus VA. So, B is at higher potential and A is at lower potential. So, VP minus VA is positive. So, it is delta V is IR. So, the potential drop here is IR. Now, these 4 points are important to understand the application of Kirchhoff's law. Now, let's see by an example what does Kirchhoff's law stand for. Suppose we have a circuit like this. In which this battery has EMF of E1 and this battery has EMF of E2. Now, this resistance is R1 and this resistance is R2. And suppose since all the elements are in series, and let us suppose that current I is flowing in this circuit. Since it is a series circuit, all the current or the current through all the elements is same, and that is equal to I. Let's not bother about the direction as of now, but what Kirchhoff's law says that since this is a loop and it is a closed loop, so if we move along this direction or if we move along this direction, the algebraic sum of potential drops has to be 0. Now let's see even if this statement is true or not. Since we are dealing with the Kirchhoff's loop law, so we have to start by some point. Let's take any point. Let's take this point. Let's take up this point as name as A. So applying Kirchhoff's loop law in this circuit or in this loop, we will start from VA, and then we will move. Let's move along the current only. So first we have VA. Now, since we are moving from lower potential to higher potential, then we have to add plus E2. Now we will go from this to this. Now, since the current always flows from higher potential to lower potential, now we are seeing with respect to this resistor only. So this part of the resistor is at higher potential and this part of the resistor is at lower potential, because we have assumed the current direction like this. We can assume also like this, but once we have assumed, stick to it while calculating throughout the question. So if this is at higher potential, this is at lower potential, that means we are moving towards lower potential. So the potential drop will be negative. So negative of I into R2. Now we have come to this point, now this point, and then this point. Now this part is at higher potential and this part is at lower potential. Again we are moving towards lower potential. So hence minus E1. Now this part is at higher potential and this part is at lower potential, because current flows from high potential to lower potential in resistor. Hence we are moving towards less potential. So potential drop is negative, minus of IR1. Now again where we reached? We reached at VA. So VA and VA gets cancelled out. So this becomes E2 minus E1 minus I times of R1 plus R2 equals to 0. This is the equation that we get from applying Kirchhoff's loop law. Now, here we would like to mention that here no one other than us has assumed the direction like this. We can also assume the direction of current like this, and we can also move anti-clockwise. The result will be same only. So this is the application of Kirchhoff law. We can analyze any complex branch or part of the circuit. Now let's do this with Ohm's law. Ohm's law says that V net equals to I into R net. Since V net is this E1 is trying to move charge in anti-clockwise direction and this E2 is trying to take charge in clockwise direction. So they both are opposing each other. Hence this becomes E1 minus E2, or else we can say E2 minus E1 also. That depends upon the magnitude, equals to I into R net. Since these two resistors are in series, we can write R net as R1 plus R2. So we can see this is equal to E1 minus E2 minus I times of R1 plus R2. Now this is equal to 0 and these both are same. Now here E2 is coming first and E1 is coming later. That is because here we have assumed that E1 is greater. But that completely depends upon the magnitude of the battery. Now we will mention one point, that this law or this loop law is based on the fact that electrostatic potential or electrostatic field is conservative in nature. Now this completes our two laws. Now we will see the application of both these laws and we will solve many problems in our next lecture. So thank you.